Ladies and gentlemen, now, we will start our first lecture of the analyze phase. The analyze phase is the third phase of the DMAIC approach. It comes after the data measurements and lead to the process improvement. In the measure phase, such key process steps have been measured, for example, flow rate, inventory level, cycle time, defect rate, etc. Data of those parameters have been gathered. The current state of the process has been fully described by the measures, and the current state map is developed. All these data and diagrams need to be analyzed and checked for their effect on process, quality, and production. We will determine variance components and assess correlation in order to find out the cause of any problem or issue. In the next phase, we will solve the problems and improve the whole process. The module will be divided into 8 lectures. These lectures including the following topics, covering the all tools and techniques using in the analyze phase, estimation of population parameters, 7 wastes in lean philosophy, cause and effect diagrams, cause and effect matrix, process mapping, 5 whys analysis, transforming data, hypothesis tests, one-way ANOVA, two-way ANOVA, correlation, regression analysis, variation analysis, design of experiments, DOE, full factorial, design of experiments, fractional factorial, design of experiments, run chart. As we mentioned before, the module will be divided in 8 lectures. It includes the following documents for download: the course material in PDF, the F distribution tables in PDF, templates for fishbone diagram, run charts, design of experiments, regression, and hypothesis test, activities and research papers in PDF files, instructional videos for ANOVA, design of experiments, hypothesis test, regression, run chart, and transforming data using Sigma XL and Minitab, instructional videos for cause and effect, process mapping using iGraphX, examples of Minitab projects for ANOVA, design of experiments, hypothesis test, regression, run chart, and transforming data. In our current case, we have a population with a known mean value mu and known or unknown standard deviation sigma. However, we want to choose random samples for testing. These samples have mean value xi and standard deviation si, where I equal to 1, 2, 3, and 4. In the estimation of population parameters, we will estimate the population mean mu using the sample mean. We often want to make a statement about the population based on a random sample taken from a population of interest. We say we want to infer a general conclusion about the population based on the sample. This is called inferential statistics. We can make a statement about the population with a certain margin of error. We saw sample-to-sample variability. Sampling error does not include other sources of error, such as those due to biased sampling, bad survey questions, or recording mistakes. We should report some kind of confidence about our estimate. Do we think it's pretty accurate? Or not so accurate? What sample size n do we need for a given level of confidence about our estimate? This has been covered in the measure phase. In the next slides, we will try to understand and learn the calculation of this estimation, error, and confidence level. The steps to estimate the population mean value mu from sample mean value x differ if the population variance is known or unknown. However, if the population variance is unknown, then we have two cases. First, sample size, n, is large, greater than or equal to 30, or sample size is small, less than 30. We will learn how to calculate the population mean value for the three cases. There are some basic information to be considered and understood very well before learn how to estimate the population parameters. The interval we will describe is called a confidence interval CI. 95% confidence intervals for the mean of a normal distribution is meaning that in the long run, only 5% of the intervals would fail to contain mu. Alpha is called a level of significant, and it is equal to 1 minus probability value of confidence value of interest. Probability of the confidence value of interest is equal to confidence level divided by 100. Then, as a result from the above, 1 minus alpha is equal to confidence level divided by 100. This is meaning that there is a probability of 1 minus alpha of selecting a sample for which the CI will contain the true value of mu. Level of significant, alpha is equal to 1 minus confidence level divided by 100. For example, for 95% confidence level, alpha is equal to 0.05. For 99% confidence level, alpha is equal to 0.01. Assume that x bar is the sample mean of a random sample of size n from a normal population with known variance. With a confidence interval of 100 times 1 minus alpha, the mean value of the population mu is given by the following equation. The equation expresses the range of the mean value of the population. Z of alpha over 2 is the upper alpha over 2 point of the standard normal distribution. The calculations will be clearer during the next exercise. ASTM, Standard E23, defines standard test methods for notch bar impact testing of metallic materials. The CHARP-EV notch, CVN, technique measures impact energy and is often used to determine whether or not a material experiences a ductile to brittle transition with decreasing temperature. 10 measurements of impact energy in joules on specimens of A238 steel cut at 60 degrees are as follows. Assume that impact energy is normally distributed with alpha equal to 1 joule. We want to find a 95% CI for mu, the mean impact energy. Please pause the lecture and solve the exercise. Alpha is equal to 0.05, alpha over 2 is equal to 0.025, z of alpha over 2 is equal to 1.96, according to the cumulative standard normal distribution table. N is equal to 10, and sigma of the population is equal to 1, and mean value of the sample is 64.46. The resulting 95% CI is found as follows. That is, based on the sample data, a range of highly plausible values for mean impact energy for A238 steel at 60 degree is between 63.84 joules and 65.08 joules. Please perform the activity and send your results by email for assessment. Assume that x bar is the sample mean, and s is the standard deviation of a random sample of size n greater than 30 from a normal population with a known variance. with a confidence interval of 100 times 1 minus alpha, the mean value of the population mu is given by the following equation. The equation expresses the range of the mean value of the population. Z of alpha over 2 is the upper alpha over 2 point of the standard normal distribution. The calculations will be clear during the next exercise. The breaking strength of yarn used in manufacturing drapery material is required to be at least 100 psi. A random sample of 36 specimens is tested, and the average breaking strength is found to be 98 psi, and the standard deviation is 2 psi. Find a 95% two-sided confidence interval on the true mean breaking strength. Please pause the lecture and solve the exercise. Alpha is equal to 0.05, alpha over 2 is equal to 0.025, z of alpha over 2 is equal to 1.96, according to the cumulative standard normal distribution table. Or, instead of searching the cumulative standard normal distribution table, we can use the Excel function norm.s.inv of alpha over 2. N equal to 36, standard deviation of the sample is equal to 2, and mean value of the sample is equal to 98. The resulting 95% CI is found as follows. The breaking strength of yarn used in manufacturing drapery material is required to be at least 100 psi, and this condition cannot be fulfilled. Please perform the activity and send your results by email for assessment. Assume that x bar is the sample mean, and s is the standard deviation of a random sample of size n, with n is less than 30. This sample has been taken from a normal population with a known variance. With a confidence interval of 100 times 1 minus alpha, the mean value of the population mu is given by the following equation. The equation expresses the range of the mean value of the population. T of alpha over 2 and n minus 1 is the upper alpha over 2 point of the t distribution, with n minus 1 degrees of freedom. The calculations will be clearer during the next exercise. An article in the journal Materials Engineering describes the results of tensile adhesion tests on 22U700 alloy specimens. The load at specimen failure, in megapascal, is as follows. We want to find a 95% CI on population mean value. Please pause the lecture and solve the exercise. Number of samples n equal to 22. Therefore, the degree of freedom of t is equal to n minus 1, which is equal to 21. T of 0.025 and 21 is 2.08 from the t distribution table. Or, instead of searching the t distribution table, we can use the Excel function t.inv of alpha and degree of freedom. The sample mean value is 13.71, and its standard deviation is 3.55. The resulting CI is between 12.14 and 15.28. The CI is fairly wide because there is a lot of variability in the tensile adhesion test measurements. It is not as easy to select a sample size n to obtain a specified length or precision of estimation for this CI as it was in the known case, because the length of the interval involves which is unknown before the data are collected. Please perform the activity and send your results by email for assessment. Seven Wastes in Lean Philosophy. The 7 wastes of lean manufacturing are what we are aiming to remove from our processes by removing the causes of these wastes. But what exactly are the 7 wastes of lean manufacturing? The 7 wastes of lean manufacturing are: 1. Inventory. Any additional inventory beyond minimal quantities is an idle resource. It takes up floor space and adds to cost. 2. Overproduction. Overproduction involves excessive use of manufacturing resources. 3. Waiting time. Waiting time requires space and adds no value. 4. Unnecessary transporting. Unnecessary transporting increases handling and increases work in process inventory. 5. Processing waste. Processing waste makes unnecessary production steps and scrap. 6. Inefficient work methods. Inefficient work methods reduce productivity, increase scrap, and increase work in process inventory. 7. Product defects. Product defects require rework, increase costs, and possible lost sales due to customer dissatisfaction. Some references add to another wastes, motion, and unused talent. The most serious of the wastes is the overproduction, which can cause all other types of wastes and results in excess inventory. Stocking too much of a product that goes unused has obvious costs: storage, wasted materials, and excessive capital tied up in useless inventory. The existence of these wastes is an indication that improvement is possible. The list of wastes also can identify potential targets for continuous improvement efforts. The Kaizen philosophy for eliminating waste is based on the following tenets. 1. Waste is the enemy, and to eliminate waste it is necessary to get the hands dirty. 2. Improvement should be done gradually and continuously. The goal is not big improvements done intermittently. 3. Everyone should be involved: top managers, middle managers, and workers. 4. Kaizen is built on a cheap strategy, and it does not require spending great sums on technology or consultants. 5. It can be applied anywhere. 6. It is supported by a visual system, a total transparency of procedures, processes, and values, making problems and waste visible to all. 7. It focuses attention where value is created. 8. It is process-oriented. 9. It stresses that the main effort of improvement should come from new thinking and a new work style. 10. The essence of organizational learning is to learn while doing. Thank you, and see you in the next lecture of Analyze phase.